Good day, everyone. We are reviewing Wetzel's Limnology textbook. This is edition number 4, and we are in chapter 11, which looks at oxygen distribution in rivers and lakes. And more specifically, today we are looking at oxygen distribution in lakes, and we'll be looking at oxygen dynamics in lakes with different mixing regime, which is subsection E. While the examples provided in figures 11-12 and 11-13 are useful for illustrating oxygen dynamics in north temperate dimictic lakes, these water bodies represent only a subset of lakes. Below, we analyze oxygen profiles from lakes with amictic, warm monomictic, cold monomictic, polymictic, meromictic, and oligomictic mixing regimes located around the globes. Amictic. The oxygen profiles in amictic Lake Bonny are marked by extremely high oxygen concentrations and consistently stratified conditions. Lake Bonny is located in Antarctica and has permanent ice cover that is 3 to 5 meters deep and very high salinity at depth. Like in other amictic lakes in this region, gases in Lake Bonny are supersaturated, resulting in oxygen concentration exceeding 200% saturation above an anoxic persaline layer. The processes that increase oxygen in the upper layers of amictic Antarctic lakes are glacial meltwater inflows in the summer, the formation of ice at the bottom of the ice sheet, which forces gases into the water, and the photosynthesis, while the process decreasing oxygen in the lower layers are ablation through the ice as bubbles, respiration, and diffusion from the meltwater perimeter of the lake in the summer. In Lake Bonny and other amictic lakes with meters of ice cover, physical processes dominate the annual oxygen budget. Due to logistical challenges, no data are available outside of the austral summer, but it is unlikely that oxygen concentrations substantively change during the year. So let's look at that a little bit here. So we have Lake Bonny here. This is on the left, we have the distribution of dissolved oxygen with depth. So depth is on the y-axis, and on the x-axis we have months from November through, like probably like maybe early February or something to that effect. And so, as they were saying in the text that we just read, is the data was only collected in the summer. So this is why it's not like a full year for the dissolved oxygen. Apparently, we do have data for temperature for Lake Bonny. So in any case, the concentration of oxygen is pretty much stable throughout these months and hasn't changed. And we can see that we have very low concentration of oxygen at depth. And then we have this sort of like a change in the concentration, so to values that are close to 50 milligrams per liter, which is pretty high. And then in temperature, it's kind of the same story, because this lake is permanently frozen. You can see the layer of ice at the top here, this white layer, and the temperature is stable. There's no like a thermocline or anything like that. Maybe like actually like in the early August to late October. It's interesting, actually. We don't have any data between November and January or late January. That's kind of interesting, which is the opposite of where we have data for dissolved oxygen. In any case, we are seeing actually a loss of temperature. Like here we have very cold temperature, and then here we have temperatures that are hovering maybe around 1 to 2 degrees centigrade. So that would be the only change that I can see. And maybe here a little bit, there is like a cooling effect in that area, which corresponds to the winter, to the onset of the winter, which is June. June is pretty much like here. June 21st would be the winter solstice in Antarctica, which is in the southern hemisphere in this case. Okay, so warm monomictic lakes. So in contrast to amictic lakes, warm monomictic lakes such as Sal Reservoir in Spain, never have any ice cover and exhibit mixing and concomitant constant oxygen concentrations throughout the vertical profile during at least part of the year. As lakes exhibit orthograde profiles are generally found in alpine or higher latitude location where ice cover is more likely. It'd be expected that warm monomictic lakes would exhibit clinograde profiles during that stratified period. Clinograde conditions are especially likely if there is a long stratified period for the warm monomictic lake, decreasing the exposure of sediments to oxygen for most of the year, as in Sal Reservoir. The brief mixing period for Sal Reservoir lasts for 1 to 2 months per year prior to the onset of stratification, with subsequent hypoxic and then anoxic conditions setting up throughout the entire hypolimnion quickly thereafter. Thus, for most of the year, Sal Reservoir oxygen profiles would be classified as clinograde, although negative heterograde curves have also been observed in some years. So let's look at this reservoir here, which would be below the one in Antarctica, and it is. So once again, like left side, dissolved oxygen, right side, temperature. So here we're in the northern hemisphere, so the warmest part of the year is the summer between July and late September. So we can see the warming effect here. We can see the presence of a thermocline here. And we don't see any thermocline in the summer, so this lake is a monomictic lake. It only turns over once. And so this is the oxygen concentration. And so what we are seeing here is that during the winter, we have pretty high oxygen concentration and a pretty even distribution, actually, pretty close to even distribution in the winter. And then with the onset of the spring, we start to see like a decrease of oxygen due to the scavenging of this oxygen by organisms throughout the lake. And then we have this clinograde, as they were talking about in the text. And so it's kind of like, and then it abruptly decreases in the late October or November time period, early November time period. Dimectic. Oxygen dynamics in dimectic north temperate lakes are discussed above at length, but we include Lake Greenwood for comparison with the other mixing regimes. Lake Greenwood exhibits classic clinograde profiles during both its winter and summer stratified periods. The lake is ice covered from November until May and exhibits anoxia near the sediment throughout most of the ice period. Interestingly, there are lower oxygen concentration at the sediment in the winter than in the summer, potentially because the winter stratified period has a longer duration, 6 months, than the summer stratified period. Greenwood exhibits substantial daily to weekly swings in oxygen in the upper layer of the lake below the ice from March until ice off in May, reflecting biological activity during this period. So this is Lake Greenwood. We can see the layers of ice that are found between mid-November to early May, and the same pattern here for the temperature. So as we know, the layer of ice prevents any thermocline to develop. So the temperature of the lake water is pretty even during the presence of an ice layer over the lake, and then we see then the warming period here during the summer, and then the presence of a thermocline. As for dissolved oxygen, as they were saying in the text, we actually see a very high anoxic period time in the winter, which is surprising. And then we see a clinograde event right here. So they were saying twice. So like in the fall, in the early summer and then in the fall. Then we have a pretty good distribution, pretty even distribution of oxygen in the early fall, and then once again we are seeing then the birth of an anoxic layer that developed here and we see that like mid-December. Cold monomictic. Oxygen profiles from Lake Abiskorsjöri in Sweden reflect typical cold monomictic dynamics, low variability throughout the year, and the presence of orthograde profiles. Abiskorsjöri is a clear water oligotrophic Arctic lake at a latitude of 68 degrees north, so that means that that lake is north of the Arctic Circle, that experiences ice from October to May. Under the ice, oxygen profiles are at or near 100% saturation. During the mixed period from July to October, some minor oxygen depletion is evident at the sediment, but the profile stays overall oxic, greater than 10 milligrams of oxygen per liter. The lack of variability in oxygen dynamic is primarily due to the low productivity in the lake, similar to Lake Waldo. Although water temperatures reach above 4 degrees centigrade in the summer, wind-driven mixing prevents thermal stratification from establishing. So this is our lake in Sweden, and we have, once again, ice layer here. So it's quite different when you look at Lake Greenwood and Lake Abiskorsjöri, and in the sense that both of them are influenced by an ice layer, but here we are not seeing in the Swedish lake, we are not seeing this change in concentration of oxygen that we are seeing in the winter here. And we are not seeing a chemocline, I guess. We're seeing slightly one here, and like a slight consumption of oxygen, and we're also seeing at the surface here, but it's pretty well distributed here. And then in temperature, there's not much going on, especially when there's an ice cover, and we do see like a warming period, but not as drastic as the lake in Greenwood. And so therefore we're not seeing a very strong, or not at all, a thermocline. And then let's look at our last lake here with a polymictic lake. Lake Kasumigara in Japan provides an example of a continuous warm polymictic lake. The lake's water column exhibits an isothermal temperature profile throughout the year, with circulation occurring near continuously due to its shallow depth and strong winds. Kasumigara is hypereutrophic, with chlorophyll A concentration exceeding 50 micrograms per liter most of the year, which explains the oxygen depletion at the sediment despite isothermal conditions. The oxygen depletion is particularly evident in the warm summer months when water temperature is greater than 20 degrees centigrade occur throughout the water column. Lake Rotorua in New Zealand is a second example of a continuous warm polymictic lake. Dissolved oxygen and temperature sensors deployed at 1 and 20 meter depth reveal brief periods of hypolimnitic anoxia during short periods of thermal stratification until continuous mixing is reestablished. So this is the lake in Japan, and here we are. So we are not. There's no ice cover during that year. This is a polymictic lake, so it turns over more than once, more than twice actually, and so in the winter, it's the dissolved oxygen is pretty even, and then starting with the spring, we are starting to see like a lowering of oxygen concentration throughout the lake, and the presence of a chemocline here. And they were saying that in the text that the presence of that chemocline, or the loss of oxygen, is due to consumption of oxygen of biota in the sediment. And then here, we are not seeing much of a thermocline per se, and it's pretty well distributed throughout the year. And but of course, it changes from close to 0 degrees centigrade all the way to 30 degrees centigrade. I mean, it's pretty high. But for any given time during that year, it's a shallow lake. It's a lake that is only like at 6 meters. It's probably why we don't have much of a stratification here. We are not seeing any stratification, and we're seeing pretty even distribution of temperature. Okay. Meromictic. Extreme cleaner grade oxygen profiles can occur in permanently stratified meromictic lakes, such as Lake Kivu, located on the border of Rwanda and the Democratic Republic of Congo. The monomolimnion receives inputs of sediment organic matter and has high concentration of reduced substances which rapidly consume any oxygen intrusion due to mixing. In Lake Kivu, the monomolimnion has very high ammonium sulfide and iron concentration, resulting in persistent anoxia. Brief partial mixing periods in the winter resulted in hypoxia at the surface, which was particularly evident in the second year of data. In comparison, increases in oxygen in the surface water in the summer was likely due to the increase in phytoplankton productivity. So we have kind of two processes kind of going on here. We have one that is using oxygen. One is the phytoplankton during the summer, and then the other is the organic matter that is degrading in the sediment and that is consuming oxygen. So let's look at that lake here. This is Lake Kivu. So Lake Kivu is right here. So this is in the tropics, or maybe very close to the equator. I haven't looked it up, but of course it doesn't freeze over. I mean, unless it was at very high altitude, which doesn't appear to be the case here. So throughout the year, we're seeing consistent, very low oxygen concentration, and that is due to the high productivity of the lake as well as the high productivity of the sediment. And then we are seeing some chemokline here going on, developing, like between pretty high at 12.5 milligrams per liter to very low, like hovering close to zero. The depth on the y-axis is about 75 to 80 meters. Temperature is pretty even, although we have like this sort of cyclical pattern, it appears. Like we have the warming period, and so therefore we have a slight thermocline, and then we have this sort of cooling period, and then etc. So that may be due to storm or to some other driver. Oligomictic, okay. Lake Maggiore, Italy, experiences complete mixing for a few weeks in the winter, only every few years. During the prolonged stratified period, the lower layer is unable to be replenished with oxygen, reinforcing a clinograde profile. Because of Lake Maggiore, relatively low productivity and subalpine location, the lake does not exhibit the extreme clinograde curves exhibited by Kivu. In the third year of data shown in figure 11-17, full mixing to the sediments occurs in March, increasing the oxygen in the lower strata until depletion becomes evident again at the sediment in August. It is notable, however, that the mixing is extremely brief and the establishment of an oxygen minimum occurs at about 150 meters and an oxygen maximum occurs at the surface, likely driven by an increase in phytoplankton productivity. So let's look at Lake Maggiore here. What is interesting is we haven't really looked at this lake, which is Lake Wetzel, which is a polymictic lake. So when we were talking about the polymictic lake, we talked about this Japanese lake, and then there's a little bit like here. Lake Wetzel is the second example of continuous, okay. So, because it's a different curve. So this lake, on the y-axis, we have the temperature, dissolved oxygen, or temperature. We have both. So, so therefore, the dissolved oxygen is in the sort of reddish lines, and then the temperatures are in the bluish line. And this is polymictic lake. And so so let's see, it's in polymictic in New Zealand. So this is the southern hemisphere, so it's going to be the opposite. So therefore, in the December time period, that's their summer, and in June, that's their winter. So so the curve then starts like right in the winter. And so in the winter, we are seeing a pretty cold temperatures, which makes sense. And so that makes sense. Although what is interesting is we have like, okay, so this is, and then we have increase, okay, right, and we have increase in temperature for the blue lines, and corresponding to the summer, the February, March time period. So here they are reporting temperatures at 1 meters and 20 meters for both, as well as dissolved oxygen. So like, for example, like dissolved oxygen at 20 meters is very low, in the summer. It's not as low at the surface as they were saying because of the influence of macrophytes at the production of oxygen from aquatic plants, where the oxygen is consumed when it's at the sediment water interface at the bottom of the lake because of microbial degradation, because of the presence of bioturbation organisms and the likes. So we are not seeing as much of a variability at depth than we are seeing at the surface than we're seeing at depth. And then in the for the temperature, it's kind of the same as well. Like at depth, we are seeing larger swings than we are seeing at the surface here. All right, so that's it for that. So now let's move on to Lake Maggiore. So Lake Maggiore is oligomictic lake, right? Yep. So it mixes very rarely. And so it appears that actually they took this data when it didn't mix, but we have a pretty even, consistent concentration of dissolved oxygen throughout the year for that lake, with the presence of a chemokline to some extent, but not as very strong. And then we have somehow like very high, higher concentration of dissolved oxygen actually for that year. So that year potentially that you may have seen some amount of turnover, although I don't see that in terms of temperature here. So temperature is pretty consistent, and below, let's say maybe 25 meters, we have the same temperature, probably about 4 to 5 degrees centigrade, and then we have these values here that there's like presence of a thermocline, a very small thermocline, although it's not really at scale. If we were looking at a scale between 0 and 50 or 75 meters, we'll probably see a little bit better. Okay, so let's look at let's see here. I think we were at Lake Maggiore. So why don't we pick it up tomorrow with horizontal variability in oxygen distribution with subsection F. Thank you for your attention, and I'll talk to you tomorrow. Bye.